In the beginning there was only chaos, that is, emptiness. Then Gaia, Earth, Tartarus, underground, and Eros, love, emerged from the void, or on their own. While Eros was there, Gaia and Tartarus, the two female gods, produced and shaped everything known in the universe. This is a story about how the universe was created in Greek mythology. But science now tells us that the universe was not created that way. Instead, the universe was formed 13.7 billion years ago as a result of an expansion called the Big Bang. The timeline that emerged with the Big Bang and later theories such as inflation, which were put forward to close the shortcomings of this theory, gives us an idea about how the Big Bang was. In the initial period known as the Singularity, the universe measured 10 to the power of negative 35 meters, and its temperature was 10 to the power of 32 degrees. During this period, the four fundamental forces, electromagnetic, gravitational, strong nuclear, and weak nuclear, were unified. From 10 to the power of negative 43 seconds to 10 to the power of negative 36 seconds, known as the Great Unification Age, gravity separated from the three other forces, and the first elementary particle and antiparticle began to form. The inflationary epoch occurred between 10 to the power of negative 36 and 10 to the power of negative 12 seconds, followed by the period known as the electro-weak epoch. The separation of the strong nuclear force triggered a cosmic inflation, causing the universe to undergo an expansion even faster than the speed of light in just a fraction of a second. During this period, the universe expanded by at least 10 to the power of 26 times, reaching the size of 10 centimeters. Quark-gluon plasma, consisting of fundamental particles from the previous era, became very finely dispersed throughout the universe. In the next era, the strong nuclear force separated from the other two, and particle interactions created a multitude of exotic particles. After that, the quark epoch began, lasting up to 10 to the power of negative 6 seconds. During this period, the temperature of the universe dropped below 10 quadrillion degrees, and the four fundamental forces assumed their present forms. When quarks and antiquarks annihilated each other, an extra quark was formed for every billion pairs. These extra quarks then combined to form matter. Following this, in a second, the age of the hadron begins, and the temperature of the universe drops below 1 trillion degrees. Under the complex conditions of this period, protons colliding with electrons combine to form neutrinos, and emit massless neutrinos that move freely at or near the speed of light in space today. The lepton period, which will last up to 3 minutes, begins. Very few of the hadrons and antihadrons, which destroyed each other during the hadron period, remain. In the next period, leptons and antileptons dominate the mass of the universe. As they collide and annihilate each other, energy in the form of photons remains. During the nucleosynthesis period, which will last up to 20 minutes, the temperature of the universe drops to the point where the nuclei of simple elements, such as hydrogen, helium, and lithium, can be formed. Almost 1 billion degrees, by combining protons and neutrons through nuclear fusion. After 20 minutes, the temperature and density of the universe drops to levels where nuclear fusion cannot continue. In the photon age, which will last from the 3rd minute to 240,000 years, the temperature of the universe continues to decrease gradually. During this long period, the universe was filled with plasma, a hot, opaque soup of atomic nuclei and electrons. After that, the universe goes through many periods, one after the other, as a result of which galaxies, stars, and our world are formed. The pressure on science for hundreds of years has finally ended in the early 20th century. Scientists from different branches of science were opening a new era in many different disciplines of science and making science shine like a diamond. But if science is shining like a diamond today, we owe it to scientists who once did not give up the path of science despite the pressure. Despite these innovations in science, some of the old current ideas were still up to date. Aristotle and some other Greek philosophers said that the universe was static, that it was an expansion or not shrinking structure, and that the world was at the center of the universe. When this assumption was accepted by the clergy and coincided with some verses in the Bible, the Church officially made the issue uncontroversial. Although this continued for a long time, Nicholas Copernicus showed that we were not the center of the universe in the middle of the 16th century. When Copernicus died in 1543, just 5 years later, another philosopher, Giordano Bruno, was born. Influenced by Copernicus's point of view, the thinker said that the world revolves around the sun with a vision far beyond the time he lived in, that space could be infinite, and that the sun would be one of countless stars. This was an incredible observation, because the telescope was not invented at that time. Bruno was convicted by the Papacy Inquisition in 1600 for his so-called perverted thoughts. Bruno, who was connected to the stake naked in the middle of the square, could not say his last word, because his tongue was tied to a metal clamp and his execution was terrible. 10 years after his death, Galileo pointed his telescope to Jupiter and observed his satellites. And his observations really supported the Copernicus model. The universe model advocated by Copernicus was the universe model in which the sun was at the center of the universe, not the Earth at the center of the universe. But almost 400 years later, the observations made by Harlow Shapley revealed that the world is not in the center of the universe, not even in the center of the Milky Way. Only 50 years ago, Darwin said that we shared the same common ancestor with the animals we underestimated. And the last observations were really an incredible coup for egoist creatures like us to learn that we were not even in the center of the Milky Way. The 20th century produced many geniuses, the most famous of whom was Einstein. Before Einstein made the innovation that would change the course of history, he faced a huge challenge. In 1915, when Albert Einstein applied his equations of general relativity to the universe, he consistently obtained the same result: a model of an expanding universe. This conflicted with the widely accepted belief at the time that the universe was static and unchanging. To reconcile this discrepancy, Einstein introduced a cosmological constant to his equations in 1917. This constant represented a repulsive force that counteracted the gravitational attraction between matter, resulting in a static universe. In 1922, a Russian mathematician mathematically demonstrated to Einstein that these equations pointed to an expanding universe. 3 years later, Hubble showed that there were more galaxies in the universe than our Milky Way galaxy, perhaps even billions of such galaxies. This news shocked the scientific community. The universe was much, much bigger than we could ever imagine. In 1929, Edwin Hubble announced the discovery that would rewrite astronomy: that the spectrum of light from distant galaxies was redshifted due to the Doppler effect. The answer was that the universe was expanding. If this observation says that everything is accelerating away from each other, it means that everything was once at one point. That discovery was one of the biggest milestones for the Big Bang. Einstein accepted the model of an expanding universe in 1931, and a year later, together with Willem de Sitter, he proposed a model of an ever-expanding universe with zero cosmological constant. Thus, one of the biggest misunderstandings in astronomy, the misconception of a static universe, which had been valid for thousands of years, was truly overcome. At the same time, the expansion of the universe gave rise to two opposing views. One was the Big Bang model published by Lemaitre, and the other was the steady-state theory proposed by Fred Hoyle and his colleagues. Hoyle argued that the universe had no beginning and no end, and that as objects moved away from each other, new objects were formed, and the energy density of the universe remained constant. As a matter of fact, it was Hoyle who gave this name to the Big Bang theory. During a live radio broadcast, he called it the Big Bang to mock this theory and so on. However, with the discovery of the cosmic microwave background radiation in 1965, Hoyle's theory lost its validity, and scientists started to use the Big Bang theory as a reference. Even though the problem of the universe's expansion was overcome, there were more problems ahead. We still didn't have enough evidence to convince us that the Big Bang really happened. It was around this time that Ukrainian physicist George Gamow and his team made the logical assumption that we know the universe is everything that exists, and that if there was such an explosion, it would not be scattered around as in a normal explosion, and therefore the heat would still exist today. The reason they said this was because they believed that in the case of such an explosion, the explosion would be confined to the universe, so it couldn't go any further than this scene. And they were right. In 1948, Gamow's students, Ralph Alpher and Robert Ehrman, argued that since this explosion occurred everywhere, the microwave radiation from the explosion should exist equally throughout the universe. This was a spectacular observation any way you look at it. In 1965, 2 young employees of Bell Telephone Laboratories in New Jersey discovered this radiation, albeit completely by accident. The microwave they picked up from their microwave antenna was at about negative 270 degrees Celsius, just 3 degrees above absolute zero, and they realized that this must be the afterglow of the Big Bang. But why were these photons at this temperature? When the universe was first born, it was filled with hot particle plasma and photons. For roughly the first 380,000 years, photons constantly interacted with free electrons. Therefore, they could not travel long distances. This meant that the early universe was opaque, like being in a fog. After this period, the universe started to expand and cool down. Because the energy or temperature was constant, but the volume was constantly expanding. The temperature dropped to about 2700 degrees Celsius, at which temperature electrons could combine with protons to form hydrogen atoms. And the temperature dropped so low that the chemical bonds they formed could not be broken again. In the absence of free electrons, photons could move through the universe unimpeded. In the billions of years that followed, as the universe expanded, the wavelengths of the photons increased to 1 millimeter, and their temperature dropped to negative 270 degrees Celsius. These photons fill the universe today, and there are about 400 of them per cubic centimeter. This creates a background radiation that can be detected by space infrared telescopes. After this discovery, it was confirmed that the intensity of microwaves at different lengths follows a black body, or thermal curve, consistent with radiation in equilibrium with its surroundings. Which is the same result that would have happened if it were the remnant of an early hot fireball phase. The photons left over from the Big Bang are still being emitted, but they are becoming fainter and less energetic as they fill a larger and larger universe. The cosmic background radiation is so frequent that each cubic centimeter contains only 300 photons, yet it accounts for 99% of the photons in the entire universe. To prove the CMB conclusively, a series of surveys were launched with the COBE satellite in 1989 and WMAP in 2001. Both confirmed our predictions more precisely, putting the age of the universe at 13.7 billion years and giving us a picture of what the universe looked like after the Big Bang. But there were still some paradoxes that needed to be resolved. Another proof of the Big Bang lies in the fact that when we look at the night sky, the sky is black. Aubert, a 19th century astronomer, asked why, if the universe is filled with billions of stars, it's not completely filled with light from these stars at night. The answer lies in the fact that light from most of these stars has not yet reached us. As incredible as the speed of light is, compared to the speed of the universe, it's a snail's pace. Galaxies and stars that have already formed are still visible to us from Earth as clouds of gas and dust. Of course, it would not be correct to say that the Big Bang was uneventful, and we need to do more research, because there's a dark matter that surrounds us, but we don't know what it is. In the 1930s, rotational velocity calculations, based on the work of Fritz Zwicky, revealed that the galaxy is actually spinning much faster than it theoretically should be in order to maintain its current equilibrium. Zwicky hypothesized that the only way this could happen was if galaxies contained much more matter than they appeared to, and that this matter had to be spread out evenly all around. Zwicky's observations were further supported by studies in the 1960s and 1970s. Rubin, one of those who conducted these studies, noted that stars near the edge of the galaxy rotate around the galactic center at the same speed as stars much closer, but stars near our sun rotate faster than others. It turns out that the force of gravity does not weaken as a star moves away from the center of the galaxy, a strong message to reconsider what we know about gravity. The explanation was that an unseen and undetectable mass was causing the increased spin. Turns out that about 85% of the mass that makes up galaxies is made up of an invisible substance known as dark matter. Unlike normal matter, it does not absorb, reflect, or emit light because it does not interact with the electromagnetic field, making it extremely difficult to detect. The researchers found the existence of dark matter from gravity on visible matter. Dark matter appears to outweigh normal matter by 1/6 and makes up 27% of the universe. The matter that makes up stars and galaxies as we know them makes up only 5% of the universe. Although dark matter is affected by gravity, it floats freely and passes through atoms of normal matter without any interference that we can detect. The strange thing is that it doesn't seem to interact with itself. It continues on its original path, even though normal matter is merged when two galaxies collide. Its existence and properties can only be inferred from visible matter radiation, and gravitational effects on the large-scale structure of the universe. Astronomers are literally fighting to detect this ubiquitous matter. They're observing everything from black dwarf stars, cold independent planets, comet-like clumps of frozen hydrogen, to tiny black holes. The Big Bang is a really great theory, but at its core there are some very important things that it has difficulty explaining. Today, we can almost guess what the universe looked like a billion years ago, but when we ask what happened in the first seconds of the Big Bang, this theory fails to give us an answer. The Big Bang is based on Einstein's theory of general relativity. General relativity doesn't work when you try to do calculations with large energies in small periods of time. The Big Bang cannot tell you how the temperature of the cosmic microwave field radiation is so homogeneously distributed throughout the universe. It can't explain how a fireball, the point where the Big Bang started, can form structures like galaxies and galaxy clusters. This seems to violate the second law of thermodynamics. If our universe started from a perfectly smooth point, then it should have continued in the same way. Today's universe would contain nothing but dark matter, with less than 1 atom per cubic meter of helium, hydrogen gas, and dark matter, with no materials such as galaxies and stars around us. The second law of thermodynamics tells us that heat moves from a hot body to a cold body, so that the temperature of both bodies eventually equalizes. Microwave background radiation discovered in the 1960s appeared to be extremely uniform, with almost no variation across the observable universe. But evidence suggested that the last time this radiation came into contact with matter was 450,000 years after the explosion. The universe would then be almost 90 million light-years across, which means that not enough time had passed for the radiation and heat to have cooled to a constant temperature, leading to a result known as the horizontal problem, which requires that the horizon should never be in causal contact with each other. Unless the universe is much smaller than we think, there should be much more diversity than there is today. The first theory of how this could happen was known as cosmic inflation, proposed by the American physicist Alan Guth in 1980. The addition of the theory of cosmic inflation to the Big Bang theory solved the horizon problem, as well as some other potential problems. This theory is the idea that the very early universe went through a period of accelerated, exponential expansion from mathematical representation of 10 to the power of negative 35 parts of a second, which can be mathematically represented as 10 to the power of negative 35 parts of a second, before coming to the slower rate of expansion that we're experiencing now. And so, the universe emerged in a microscopic region. Even though the universe has been expanding since the first explosion, inflation is that the universe followed before inflation in a very short time and increased much faster than it would follow after this period. Some calculations say that this inflation would be 10 to the power of positivity 26. That is from the size of a proton to about the size of a grapefruit. This is such a big number that if you were to grow in this way, you could easily reach the moon from where you're sitting at the beginning of this growth. We know that growth in this short period of time is much greater than the speed of light. The explanation for how this is possible is that the universe is not expanding in one direction. If two airplanes were moving in different directions at 1,000 kilometers per hour, they would be moving away from each other at 2,000 kilometers per hour. From another point of view, the speed of light is a limit for the contents of the universe, not for the universe. Science is still trying to answer what caused this inflation, but the best guess is vacuum pressure, triggered by the separation of the strong nuclear force from the other forces. The symmetry breaking caused by this separation is believed to have charged the universe with much more energy than it would have otherwise had, leaving it in a highly unstable state with a sharp outward anti-gravity, which smoothed out much of the disorder in the existing matter and created large quantities of particles in a very short period of time. This theory allows for quantum fluctuations, a kind of disorder at the subatomic scale during an early stage of the expansion of the universe, which provides the starting point for the large-scale structures we see in the universe today. But what about the shape of the universe? I'll talk about it a little later, but the universe can have different shapes. According to research, the shape of the universe is flat. Guth explained this is due to the vastness of the universe. It's like when we look at the Earth from its surface. We don't perceive the shape of the Earth and think it's flat. But the universe could still be shaped in two different ways. So even though the observable universe appears to be flat, the shape of the whole universe could be different. Also, even though there are many magnetic monopoles in the inflationary universe, the chances of observing them in such a universe are extremely low. So, Guth solved 3 problems that the Big Bang Theory could not solve. His answer to the flatness problem was the size of the universe. His answer to the horizon problem was that regions that seem far apart now were in contact with each other during this inflation period, and his answer to the monopoly problem was that we were less likely to observe these monopoles due to the huge size of the universe. The amount of variation in the cosmic microwave background radiation predicted by Guth's theory was precisely confirmed by the COBE satellite. WMAP revealed this change much more precisely. In 2014, astronomers announced that they had found and mapped gravitational waves in the cosmic microwave background radiation. These observations provided real evidence for the theory of cosmic inflation. Though Guth could not find a way to end inflation for the formation of stars, he had put forward a very influential theory. Many refinements to Guth's theories have been and continue to be made. Dark matter and cosmic inflation provide support for the Big Bang Theory, but there are still some complex problems with the theory. While the universe is expanding every second, gravity is trying to reverse the situation by interacting with matter. This raises 2 possibilities. One is that the universe contains enough matter for gravity to stop or even reverse the expansion, leading to what is known as the Big Crunch theory. In the other case, the universe continues to expand forever. According to the general theory of relativity, dividing the average density of the universe by the density required for the universe to have 0 curvature, omega, indicates a closed or spherical universe if it's greater than 1, a flat universe if omega is equal to 1, and a saddle-shaped universe if omega is less than 1. The cosmic inflation model assumes that omega is exactly 1. But according to this model, the universe will one day, after an infinite amount of time, stop expanding. But for that to happen, the universe would have to reach a critical density of matter, which is about 5 atoms per cubic meter. This may seem an absurdly small number to you, but when we take into account the gas and even dark matter between stars and galaxies in the visible universe, we can only reach about a quarter of the required critical mass. But in 1998, 2 separate astronomers observing Type 1, a supernova, made troubling discoveries about critical mass in the expanding universe. The explosions in the supernova were slower than we expected, suggesting that the explosions were further away from Earth than expected. In other words, since the supernova exploded, the universe has not been expanding faster than we thought it was expanding. In other words, the rate of expansion has been increasing by the minute. The cause of this acceleration was attributed to space itself. This finding suggests that space contains dark energy or a kind of anti-gravity force that we cannot detect. So even what appears to be a vacuum actually contains a mysterious energy that we don't know about. Some calculations made by NASA show that 73 or 74% of the universe is composed of this dark energy. The intriguing part is that almost 75% of the total mass of the universe is made up of dark energy. About 85% of the remaining matter is made up of dark matter, which means that everything we can detect that actually makes up the universe only makes up about 4% of the universe. When we include dark energy in the revised Big Bang model, we can properly account for the missing 3/4 of the universe that caused the observed acceleration in this model. Fortunately, we can't yet precisely explain what dark matter and dark energy are, or how they work. It appears to be uniformly distributed in space, generating negative pressure and pushing galaxies further apart. The effects of dark matter are more pronounced as the distances between galaxies increase, but they seem to be absent in regions where gravitation is dominant. Although there are observations and suggestions about what dark matter and energy are, we have yet to find a result that can be taken seriously at the scientific level. The fundamental laws of physics are not yet advanced enough to answer this question. Scientists believe that the end of the universe depends on the shape of the universe, how much dark energy it contains, how the density of dark energy reacts to the expansion of the universe, according to the equation of state. If the geometry of the universe is closed, like the surface of a sphere, then there are 2 main possibilities. If our universe has very large amounts of dark energy, then our universe could theoretically continue to expand forever. But if the universe lacks the driving force of dark energy, gravity will eventually stop expanding, and all matter in the universe will begin to contract until it reaches the final singularity known as the Big Crunch, somewhere around 100 billion years from now. In this scenario, the universe will shrink uniformly at first, then gradually increase in size. In the final stages, when the universe is compressed into a very small volume, as the singularity approaches, the bending of space-time will become so violent and chaotic that space and time will actually shatter into droplets. and existing terms like time and space will lose their meaning. This model offers the possibility that the universe was reborn again in a new Big Bang, but the latest findings from the 1990s make this outcome unlikely. If the shape of our universe is flat or open, and even in the absence of dark energy, a negatively curved universe will continue to expand forever, and gravity will slow down the expansion. With the introduction of dark energy into the equation, the expansion would not only continue, but also accelerate, and how things unfold depends on the property of dark energy, which is a mystery to us. Another possibility is that the acceleration caused by dark energy will increase indefinitely. Eventually, dark energy will become so strong that it will completely overwhelm the effects of gravity, electromagnetic, and weak nuclear forces. Known as the Big Rip, this would result in the disintegration of galaxies, stars, and atoms, and the universe would end in a relatively short period of time, only 50 billion years. The most likely outcome, however, is a long, slow death known as the Big Freeze. The universe continues to expand and gradually falls into a state of zero thermodynamic free energy, unable to sustain motion and life. Very close to absolute zero, all that will be left will be dead stars, black holes, and cold dead planets. Eventually, as protons and neutrons decay into positrons and electrons, even the atoms that make up the remaining matter will begin to disintegrate, destroying each other over time. In 10 to the power 116 years from now, even positroniums will have collapsed, and the particles will have destroyed each other. In this way, all matter will slowly evaporate as weak energy, leaving only black holes that will spread across the vast expanse of the expanding universe. The black holes will die out, and in 10 to the power of 200 years from now, there will be only empty space and radiation left in the universe. Time will lose all meaning, as there will be nothing to take as a reference. Despite all these scary stories and mysteries, the universe is a truly amazing place, yet so much of the universe remains a mystery, waiting to be solved somewhere. Who knows? Maybe one of us will solve this mystery.